Category O, Lecture 18, Enright's completion. We start this lecture with recalling some generalities about OR localization. Let R be a ring and S a multiplicative subset of R. We recall that the pair R and S satisfies the right OR condition, provided that for any element little r in R and any element little s in S, the intersection of the sets little s times big R and little r times big S is non-empty. If a pair R and S satisfies the right OR condition, we can define the right OR localization of R with respect to S. This is defined as a quotient of the Cartesian product of R and S by the equivalence relation given as follows. Two pairs R, S and R prime, S prime are equivalent if there are elements S tilde in S and R tilde in R such that S prime times S tilde are equal to S times R tilde and R prime S tilde is equal to R tilde. So in this localization, the pair R, S is interpreted as the element R times S inverse. Left OR condition and left OR localization are defined similarly. The main property of OR localization, when it exists, is that this localization is a universal initial object in the category whose objects are all possible pairs Q, phi, where Q is a ring and phi from R to Q is a morphism of rings such that the image phi of S is invertible for any element S in S. And morphisms in this category are defined as follows. A morphism from the pair Q, phi to the pair Q prime, phi prime is a ring homomorphism alpha from Q to Q prime such that alpha composition with phi is equal to phi prime. Let us now discuss localization of the universal enveloping algebra with respect to a root. Let G be a semi-simple finite-dimensional complex Lie algebra with a fixed Cartan subalgebra H. So fixing this Cartan subalgebra gives rise to a root space decomposition of G into a direct sum of H and the root spaces G alpha, where alpha runs through the root system phi of G with respect to H. Let us fix a root alpha in phi and a non-zero element x alpha in the root space G alpha. Note that the root space is one-dimensional, so the element x alpha is defined uniquely up to a non-zero scalar. Lemma: the set S of all powers of the element x alpha satisfies both left and right OR condition in the algebra U of G. To prove this, we first note that the adjoint operator of x alpha acts locally nilpotently on the Lie algebra G. From Leibniz's rule, it follows that this element also acts locally nilpotently on the universal enveloping algebra U of G. Now, given an element U in U of G, we can rewrite the identity that some power k of the adjoint element of x alpha applied to U is equal to 0 in the form that x alpha times some element U prime is equal to U times some element S prime, exactly as requested by the OR condition. So how this works is best seen on an example. Assumes that the second power of S applied to U is 0. So the second power of S applied to U is S squared U minus 2 SUS plus US squared, and this is equal to 0. So now if we move the last term to the right and take in the first term S out on the left, we get the expression S times minus SU plus 2US is equal to U times S squared, exactly as claimed. So therefore, we can form the corresponding OR localization of the universal enveloping algebra with respect to x alpha, and we denote this localization by u alpha. Note that, directly from the construction, u of g is a subalgebra of u alpha. So here is an easy SL2 example. So if you consider the Lie algebra SL2, it has a standard basis given by the lower triangular matrix F, diagonal matrix H, and the upper triangular matrix E. So the universal enveloping algebra of SL2 has a PBW basis consisting of all standard monomials of the form f to the power I, h to the power j, e to the power k. So the product of these elements where I, j, and k are non-negative integers. If we choose the root alpha such that it corresponds to the element f, then an analog of the Poincare-Birkhoff-Witt basis for u of alpha will consist of monomials of the form f to the power I, h to the power j, e to the power k, so the product of these elements, where now I is an integer, while j and k are non-negative integers. So we have inverted the element f. It is easy to see that in the algebra U of alpha, we have the following relations. We have the obvious relation that f and f inverse are inverses of each other. Then we have the relation h f inverse minus f inverse h is equal to 2 f inverse. So we should take the commutation relation between h and f and multiply it with an f inverse on both sides to obtain this one. We also have the relation that f inverse e minus ef inverse is equal to f to the power minus 2 times h plus 2, or h minus 2 times f to the power minus 2. So for this, we take the commutation relation between E and F and multiply it with F inverse on both sides, and also use the second relation. From this description of bases in the algebra U of SL2 and U of alpha, we can observe that the algebra U of alpha is not free over U of SL2. So next, we discuss the functor of taking a locally finite part of a module. We work in the same setup as above. So we have our algebra G, a fixed root alpha, and a fixed non-zero element x alpha in the corresponding root subspace. Definition. Given a G module M, we denote by L alpha of M the subset of M consisting of all elements V which are killed by a big enough power of the element x alpha. Claim L alpha of M is a G submodule of M. Directly from the definition, it is clear that this is a subspace of M, so we only need to check that it is stable under the action of the universal enveloping algebra. Given an element U from the universal enveloping algebra, we know that there is some positive integer n such that the nth power of the adjoint operator of x alpha applied to U is equal to 0. Therefore, given an element V in M, which is killed by the case power of x of alpha, we can do the following computation. If we apply the power n plus k plus 1 of the element x alpha to the image of V under U, so we can move x alpha past U using the adjoint action and rewrite this as a sum over all I, some complex coefficient Ci, it should be some kind of binomial coefficient, plus minus, then the i's power of the adjoint action of x alpha applied to U, and then x alpha to the power n plus k plus 1 minus I applied to V. And since our power n plus k plus 1 is chosen to be very big, then either the image of V under this power of x is 0, or alternatively, the i's power of the adjoint operator of x alpha applied to U is 0. So all summands of this big direct sum are 0, so we get 0, which proves our lemma. Given a homomorphism phi from M to N, we can restrict phi to L alpha of M, and it is clear that the image of L alpha of M under phi will be a submodule of L alpha of N. Therefore, L alpha is an endofunctor of G mod. Please note that L alpha is a subfunctor of the identity functor by definition. Now we can define Enright's completion functor associated to alpha. So definition, Enright's completion corresponding to the root alpha is defined as the endofunctor of G mod, which is a composition of first tensor induction from UG to U minus alpha, and then taking the locally finite part L alpha. Due to the fact that U of G is a domain, U minus alpha is flat over U of G, and hence the tensor induction functor from U of G to U minus alpha is exact. Being a subfunctor of the identity functor, the functor L alpha is easily seen to be left exact. Unfortunately, it is not exact in general. From these two observations, it follows that the functor E alpha is in general left exact. So this functor is inspired by the 1979 paper by Enright, where a slightly different version of this functor was considered. Let us do an SL2 example. We consider the algebra SL2, we take the root alpha which corresponds to E, and then the root minus alpha corresponds to F. So please note that Enright's completion E alpha is defined using an interplay between minus alpha and alpha. So we localize with respect to minus alpha, and then we take the locally finite part for the action of alpha. So let us start with the Verma module delta minus 2. So we draw the picture of delta minus 2, where basis elements correspond to their weights. The action of F is given by arrows to the left, which are in magenta. The diagonal action of H is given by violet loops for each weight space, and the action of E is given by teal arrows, which go to the right. So the arrow represents a non-zero action of the corresponding element. So the module delta minus 2 looks as follows. And if we localize the action of F, so we localize with respect to minus alpha, which corresponds to F, localizing with respect to F, we make the action of F invertible. So the outcome will be this module. So the action of F on the original module is injective, but minus 2 doesn't have a preimage. So we have to add the preimage of minus 2, the preimage of the preimage of minus 2, and so on. So the localized module will look as follows. And now in this module, we should take the part which is locally finite with respect to the action of E. And we see that this part consists of all original elements, the original submodule delta minus 2, but we also add the element of weight 0. So on weights 2, 4, and so on, the element E acts locally injectively. In other words, the Enright completion of delta minus 2 for SL2 is delta 0. So let us now take a look at the second Verma module in the principal block of for SL2, which is delta 0. So delta 0 looks as follows. If we complete it, we again first localize. The action of F is injective, but not surjective. So we have to add the preimage of 0, then the preimage of the preimage of 0, and so on. We end up with this module, and this is the same module which we obtained after the localization of delta minus 2. So taking the locally finite part, we again end up with delta 0. So the conclusion is that Enright's completion of both delta minus 2 and delta 0, both these Enright's completions are isomorphic to delta 0. Now let us discuss Enright's completion as an endofunctor of category O. So let us fix a triangular decomposition of G into a direct sum of H, and the negative part and minus, and the positive part and plus. Recall that the BGG category O associated to this triangular decomposition consists of all finitely generated, H diagonalizable, and locally un plus finite G modules. So in order to be able to speak about Enright completion on category O, we need to fix a simple root alpha. For non-simple roots, the corresponding Enright completion does not preserve category O. So we will take a simple root alpha. And the claim which we want to discuss is that the corresponding Enright completion E alpha restricts to category O. First observation, we claim that E alpha sends weight modules to weight modules. Of course, we only need to check that when we localize, then the new elements which we produce, and we produce them by applying the inverse of the element x minus alpha, that application of this kind of elements sends weight vectors to weight vectors. But this follows directly from the relation which we saw in the example of SL2, the relation that H and F inverse commute up to adding some scalars to H. So we have this kind of relation between any Cartan element and this new element x minus alpha to the power minus 1, and this relation ensures that these our new localized elements send weight vectors to weight vectors. So when we start from a weight module, we localize it, we will get a weight module. The next thing which we need to discuss is that if we have a module in O and we localize it, then the resulting module has finite dimensional weight spaces. To prove this, we first observe that any weight in the localized module, so we know that the localized module is a weight module, so if we have a weight of a localized module, then this weight has a form, a weight from the original module plus an integral multiple of alpha, or actually a multiple of alpha with coefficient which is a non-negative integer. One can show that if we consider a module M in O, then the dimensions of all weight spaces of M, which have the form fixed weight lambda and then plus k alpha, where k is an integer, if we consider all such weights of M, then the dimensions of the corresponding weight spaces are uniformly bounded. This is easy to prove for Verma modules because their dimensions of weight spaces are given by Constant's partition function, and it is easy to see that Constant's partition function stabilizes if you add a multiple of a simple root. Then from Verma modules we can deduce it for simple modules, and then we can deduce it for all modules because all modules in O have finite lengths. So now the claim of the observation follows from the construction of the localization. So when we localize, what we do, all elements on which x minus alpha acts locally nilpotently, they will be killed. And all elements on which all powers of x minus alpha act locally injectively, we need to add preimages of such elements. However, the dimension of the space of such elements is of course bounded by the uniform dimension of weight spaces of this form. This implies the claim of the observation. As a consequence of this, if we start from a module in O and take its Enright completion, we will get a weight module with finite dimensional weight spaces. Indeed, Enright's completion of M is by definition a submodule of this localization. Next, we discuss the property that Enright's completion send modules in O to UN plus locally finite modules. Let us denote by Q the set of all linear combinations of positive roots of G with non-negative integer coefficients. Then, for any weight lambda of a module M in O, the intersection of the support of this module with the set lambda plus Q is finite. Denote by Q alpha the set of all linear combinations of all positive roots of G except alpha with non-negative integer coefficients. Since any weight of the localized module is of the form lambda plus k alpha for some weight lambda of the original module and some non-negative integer k, it follows that for any weight of the localized module, the intersection of the support of the localized module with the set lambda plus q alpha is finite. Also, by definition, G alpha acts locally finitely on the Enright completion of n. So if we denote by n the subalgebra of n plus generated by all G beta, where beta is a positive root but not alpha, then as a vector space using the PBW theorem, the algebra un plus can be decomposed as a tensor product of un and u of g alpha. And now we see that G alpha acts locally nilpotently, while UN definitely acts locally finitely. Combining this with observation 2, we get the necessary claim of observation 3. Finally, let us prove that Enright's completion restricts to category O. It remains to show that for any module M in O, its Enright completion has finite length. So due to left exactness, we can of course assume that M is a simple module. So it's of the form L lambda for some lambda. Note that the center of the universal enveloping algebra commutes with any element in the universal enveloping algebra, in particular with the element x minus alpha. But then it also commutes with the inverse of this element. This means that the Enright's completion of L lambda has the same central character as the module L lambda. So the action of the center on the Enright's completion is the same as on the original module. In other words, if some element of the center kills the original module, it also kills the Enright's completion of the module. So since the Enright's completion is a weight module and it is locally un plus finite, each simple subquotient of this module is of the form L mu, where mu is a weight. But then, since the central character is preserved, we obtain that mu must belong to the dot orbit of lambda, and since we already know that Enright's completion has finite dimensional weight spaces, we get that it must have also finite lengths. From now on, we denote by E alpha the restriction of Enright's completion to category O. We will only work with Enright's completion in the setup of the category O. We claim that the embedding of U of G into the localization U minus alpha gives rise to a natural transformation, which we denote epsilon of alpha, from the identity functor theta E on O to the Enright's completion functor E alpha. Proof: if M is an object in O, then the embedding of U of G into U minus alpha gives rise to a homomorphism phi from M to its localization. Since M belongs to O, G alpha already acts locally nilpotently on M. Therefore, it also acts locally nilpotently on phi of M. Therefore, phi of M belongs to L alpha of the localization of M. And hence we can define epsilon alpha evaluated at M as the restriction of phi to the Enright's completion of M. Also, we have that the kernel of this natural transformation is the set of all elements in M on which G minus alpha acts locally nilpotently. Clearly, this is exactly the part of M which is killed when we localize our module M. A very important property of Enright's completion is the following property, which I usually call the SL2 nature of Enright's completion. Let us denote by A the SL2 subalgebra of G generated by G plus minus alpha. And let us also denote by E alpha upper A the corresponding Enright's completion functor for this algebra A. I claim that the following diagram commutes up to an isomorphism of functors. We can start from category O0 for our algebra G and write completed and then restrict to the algebra A. Alternatively, we can first restrict it to the algebra A and then Enright complete the outcome, but now as an A module. And the claim is that these two different ways to go around this diagram commute up to a natural isomorphism. Of course, it is enough to prove the claim for the corresponding localization functors in the place of Enright's completion functors. For the localization functors, one way around the diagram, this way, corresponds to tensoring with the AG bimodule U minus alpha. The other way around the diagram, this way, corresponds to tensoring with the AG bimodule given by tensor product over U of A of the localization U of A with respect to minus alpha and the AG bimodule U of G. Using the Poincare-Birkhoff-Witz theorem, it is very easy to see that the multiplication map from this tensor product to U minus alpha gives rise to an isomorphism of AG bimodules. And this implies the necessary claim. Let us now do a complete SL2 example. So since F acts nilpotently on LE, the Enright's completion kills LE. We have already computed Enright's completion of delta minus 2. So this is a simple module LS. So if we start from this module, we first localize, we get this kind of module. And when we take the locally E-finite part, we get the Verma module delta E. And similarly, we have computed that Enright's completion of delta E gives delta E. So next, the claim is that Enright's completion of nabla E gives delta E. So indeed, when we localize, the LE submodule is killed, and then the localization of LS gives us this module just like for LS, and then taking the locally finite part gives us delta E. Finally, Enright's completion of the big projective module PS is isomorphic to PS. This projective module has the following picture. So it has one-dimensional zero subspace and all others are two-dimensional. It has two copies of delta S in its composition series. When we localize, we get such a picture. So we add a copy of a big projective module in category O for the other Borel subalgebra. And the element E doesn't act locally nilpotently on any of the elements in this new module. So the locally finite part will give us our original module back. And similar computations actually show that Enright's completion of any Verma module, so any Verma module with highest weight which is not integer or equal to -1, gives us back our Verma module. So next, we claim that the functor E alpha is idempotent. Consider the parabolic subalgebra of G given by adding to the Borel subalgebra H plus N plus the root space G minus alpha. Consider the corresponding parabolic category OP. Recall that we have the dual Zuckerman functor ZP hat, which is defined as taking the maximal submodule of a module which belongs to our parabolic category. Then directly from the definition, so the parabolic category is a category where G minus alpha acts locally finitely. So directly from the definition, it follows that this dual Zuckerman functor is exactly the kernel of the natural transformation from the identity to Enright's completion E alpha. So now we are ready to prove that Enright's completion is idempotent. So it's a left exact functor, so we can apply this left exact functor to the left exact sequence. 0 goes to Z alpha hat, goes to the identity, goes to E alpha. Let us also note that E alpha kills Z alpha hat. This we saw, so this is a part which is killed by the localization. Therefore, from the left exactness of E alpha, we get an inclusion of E alpha into E alpha squared. To check that this inclusion gives rise to an isomorphism of functors, we just need to compare the characters of the module E alpha M and E alpha composed with E alpha M. So we need to prove that these two characters coincide for any module M. But because of the SL2 nature of Enright's completion, this can be reduced to the SL2 case. And if we go to the SL2 case, we see that for any module which appears in the image of the Enright's functor, its completion coincides with this module. So it's only delta E and PS which appears in the image, and in both cases, the completion gives this module back. So this implies this property that Enright's completion is idempotent. Next, let us discuss the interplay of Enright's completion with a simple preserving duality star on O0. So let us define E alpha hat as a conjugation of E alpha by the simple preserving duality. Of course, directly from the definition, it follows that E alpha hat is a right exact functor. So conjugating the left exact sequence, 0 goes to the dual Zuckerman, goes to the identity, goes to the Enright completion. So conjugating this sequence by duality, we get the left exact sequence where the functor E alpha hat is mapped to the identity, and the cokernel is exactly the usual Zuckerman functor Z alpha. So we claim that the composition of E alpha after E alpha hat is isomorphic to E alpha. To prove this, we apply E alpha to the natural transformation from E alpha hat to the identity. So this gives us a natural transformation from E alpha after E alpha hat to E alpha. Again, using the SL2 nature of E alpha, we just need to check that in the case of SL2, this natural transformation is an isomorphism of functors. And this is again a direct check on this example. So dually, we also have that E alpha hat after E alpha is isomorphic to E alpha hat. One consequence of this is that the pair E alpha hat E alpha is an adjoint pair of functors. We have just seen that the composition of E alpha hat after E alpha is isomorphic to E alpha hat. And we have a natural transformation from E alpha hat to the identity. So this gives us a natural transformation from this composition E alpha hat after E alpha to the identity. Dually, we know that E alpha after E alpha hat is E alpha, and we have a natural transformation from the identity to E alpha. So this gives us a natural transformation from the identity to the composition E alpha after E alpha hat. So these are our adjunction morphisms. So from what we already proved, we see that if we take the composition E alpha after E alpha hat after E alpha, so then the first thing compresses to E alpha, and then we use that E alpha is idempotent, we get E alpha. And we have a similar dual relation E alpha hat after E alpha hat is isomorphic to E alpha hat. So using this and our adjunction morphisms, one directly checks the adjunction identities for this pair of functors. So this implies the proposition that E alpha hat and E alpha is an adjoint pair of functors. Our next observation is what happens if we complete projective modules. Please note that completion is a left exact functor, so it is uniquely defined on injective modules. It is not usually uniquely defined on what it does to projective modules. So the claim is that the functor E alpha restricts to the category of projective objects in O0, and this restriction is isomorphic to the identity functor. Proof. Let us take a projective module P in O0. Note that the restriction of P to our SL2 subalgebra A is an infinite direct sum of projective modules in the category O for A. And now we can check the SL2 computation and see that in that case, completing a projective module always results in the same module. And also that the natural transformation from E alpha to the identity is actually an isomorphism in the case of SL2. Because of the SL2 nature of Enright's completion, we deduce that the restriction of the natural transformation E alpha to P is an isomorphism, which implies our proposition. Dually, of course, the functor E alpha hat restricts to the category of injective objects, and this restriction is isomorphic to the identity functor. So this is just obtained from the previous proposition using the simple preserving duality. Let us now compute derived completion in the case of SL2. Injective modules are, of course, acyclic for left exact functors, so if we apply the derived version of Enright's completion to injective module, it's the same as applying the functor itself. And we have already computed that completing IE, we get PE, and completing IS, we get IS back, which is the same as PS. So here's how we compute derived completion of LE. So we take the injective resolution of LE. So LE is in IE, the cokernel S is inside IS, and then the cokernel is IE back. So now when we apply the Enright's completion, the IE goes to PE here, the IS remains the same, and the IE here also goes to PE here. So we get this complex, and it has homology E in homological position 2. And also we can see that it goes 4 steps up in the gradient. So here is how we compute the derived completion of LS. So LS has injective resolution. It's a submodule of IS, and the cokernel is IE. So when we complete, IS remains the same, and IE becomes PE. So in the homological position 0, we get additional homology. So LS is mapped to delta E. And in the homological position 1, we get homology E. And finally, here is a computation of the derived completion of the projective module delta E. So delta E has the following injective resolution. It's a submodule of IS. The cokernel is a submodule of IS, and then the final cokernel is IE. So if we apply completion, the two IS's remain the same, and IE goes to PE. And now we see that delta E, of course, remains in its homology. Completing projectives is the identity on projectives. But then we get a new homology E in the homological position 1 and a new homology E in the homological position 2. So this is a computation how derived completion operates for the algebra SL2. But this has several consequences. So the first thing, which is very easy to observe from this computation, is that for the Lie algebra SL2, injectives are the only acyclic objects for the Enright's completion, and projectives are the only acyclic objects for the dual of the Enright's completion. Another thing which we can observe is that E alpha sends any object to an E alpha hat acyclic object, and vice versa, again in the case of SL2. From this and the SL2 nature of Enright's completion, it follows that for any G, E alpha sends any object to an E alpha hat acyclic object, and vice versa. Now we claim that the right derived of E alpha is a self-equivalence of the bounded derived category of O with inverse left derived of E alpha hat. Proof. Let P be a projective module. So if we compute the composition of taking first the left derived of E alpha hat and applying it to P, and then taking the right derived of E alpha, E alpha hat is itself acyclic on P, so we can just apply E alpha hat, but then this image is acyclic for E alpha, so we can delete R as well. But then E alpha after E alpha hat is just E alpha, and E alpha is identity on P. This implies that the composition of R E alpha after L E alpha hat is the identity on the bounded derived category. And usually we prove that the composition in the opposite order is the identity on the bounded derived category when we use injective modules. Let us finish with a couple of questions for PhD students. Question number 1, prove that then the functor L alpha of gmode is left exact and that it is not exact in general. Question 2, Prove that for any module M in O, and for any weight lambda of this module, the dimensions of the weight spaces of M for weights of the form lambda plus k alpha, where k is an integer, are uniformly bounded. Question number 3. Prove that the ice homology functor of E alpha is 0 if I is greater than 2. Question number 4. Check directly the adjunction identities for the pair E alpha hat E alpha in the case G is equal to SL2. Question number 5. Let P be a parabolic subalgebra of G with Levy factor A. Prove that the restriction to A of any projective module P in O0 is an infinite direct sum of projective modules in the category O for A. Thank you very much and see you next time.